Hi, I'm Professor Seth Chandler from the University of Houston Law Center, and this video is on p-hacking. It's part of the course Analytic Methods for Lawyers. As I mentioned in the abstract, this essay and video is really inspired by watching too many baseball games in which the broadcasters fill time with statistics. Ryan's done particularly well against Jones with 5 hits and 11 at-bats. And those sort of statistics are extremely unlikely to pass any sort of chi-square analysis, and so that's always bothered me. But also, the problem with a lot of modern data is there is so much modern data that you can almost always find, quote, significant, close quote, relationships. But it turns out that those relationships are illusory. And this may in part be why some recent scholars have concluded that most published research, although not their own, is false. So, this video is going to explore why is it the case that we're so vulnerable to p-hacking, how do we do it, and how do we defend against it. Let's start by creating completely meaningless data. So imagine we have 100 binary variables. They might be to pursue the baseball setting, whether the game was played at night, or whether it was after the 6th inning, or whether the game was on artificial turf, or whether there were runners in scoring position, or whether the player had gotten a hit on a previous at-bat, or whether the pitcher was left-handed, or whether it was a relief pitcher, or whether it was in a national league. There are just hundreds of these categories that exist in baseball, and one can imagine the same thing for a chemical plant or use of a website. In the modern world, we do not starve for data. So what I want to do is to create 10,000 rows of 100 binary variables that are going to be selected from this coin flip distribution. Those will be our covariates, sometimes called independent variables or features, and we'll just postfix the result with dimensions. So there you go, 10,000 by 100 pieces of data. And now, imagine there are 100 outcomes you could measure for each row of the data, like did the batter get a hit, or did they hit a home run, or did they strike out, or did any runners advance, or did anyone score, or was the ball hit to left field, or just many, many things. And similarly, in some sort of chemical plant, did the chemical flow out of the tube, and at what rate did it flow out of this tube or that tube? And so I really think it's not too hard to imagine 100 outcomes from 100 scenarios, 100 pieces of data. So I'm going to simulate that by just having a random variable drawn from a normal distribution, and we'll have 10,000 by 100. So we've got 100 pieces of input and 100 pieces of output, and in both instances we have 10,000 examples. All right, so we've got another 10,000 by 100 data set. Now let's do some multiple linear regression. I'm not going to do anything fancy. I'm just going to take that 10,000 by 100 covariate matrix and say that what we're trying to do is to predict the first column of y. That's this part notation here. We're going to take all the rows of y, but just the first column. So we will thread those together, and so we will now have a matrix that is 10,000 by 101, 100 covariates, and one thing we're trying to predict. And then we're going to use linear model fit on that. Here's a list of basis functions, x sub 1, x sub 2, x sub 3, dot, 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 x sub 100, and a list of variables, x sub 1, x sub 2, x sub 3, dot, 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 x 100. Maybe we haven't seen array before. Let's actually look at that. Here's array of x5, and it's just going to create, it's almost as if it is applying the function x to a range from 1 to 5. You could also have it could be 5 by 3, and then you're going to create a matrix. Let's show this in matrix form. And a matrix of variables. So it's just a convenient way of creating numbered variables. All right, and so now let's execute this code. We'll run our linear model fit on our data, and we get a fitted model. All right, well, let's get the p-values for each of the non-intercept parameters. And just let's do something you might feel more comfortable with. We've done parameter table before, and you can see that what we have is a bunch of estimates, standard errors, t-statistics, and p-values for each of the covariates. But what I'm really interested at the moment in is just the p-values. And so I'm going to use a property we may not have seen before, but it just extracts the p-values. So let's just see what that is. Okay. So it's just a list of numbers, and what you'll see here is I'm using rest. Rest says take the rest. Don't take the first one, just take the rest, because the first one relates to the intercept coefficient, and I'm not so interested in the intercept coefficient. And we have our friend terse, so we have a short output. All right, so there are our parameter p-values. And now let's see how many of those p-values, even though our data is meaningless, even though there is no relation, it's all noise, even though there's no relationship between the covariates and the y-value, let's see how many variables appear to have a p-value that's, statistically significant. And it turns out there are 4, which, if you think about it, isn't all that surprising, because what does a p-value of 0.05 mean? It means that if the null hypothesis were true, there would only be a 5% probability that you would see a coefficient as large as you do. And so therefore, 4 is roughly 5% of 100. And so in some sense, it's not surprising that you're going to see 4 false positives here. Okay? So we can write a little function that automates this process, and we can write one that works properly. Okay, that looks good. So all this is doing is it's automating what I just did, and so we can replicate. I changed the variable names at some point in producing this notebook, so that's the reason that I'm tweaking here. So we can see that just replicates what we just did. I've just automated the process by creating a function false positives. So let's look now. What we just did before was to take our 100 covariates and use that to predict the first column of y. But there's no reason to restrict ourselves to the first column of y. We could try to predict the second column of y, and the third, and the fourth, and the fifth, up to 100 columns of y, and we could compute the number of false positives. So what we're going to be doing now is 100 different linear regressions, and what we're going to get is the number of false positive readings in each of those 100 linear regressions. So this does take a little bit of time. I've attached what's called a monitor to the computation where it will track which regression we are up to. So this little, what we should see is, well, I'll show it to you and you'll see it. So we're up to regression 6, 7, 8, 9, 10, etc. Chugging along, chunka, and I'll probably cut this out of the video. 95, 96, 90. All right, we're done. So here are the number of false positives we got. Could make a histogram of that, I suppose. And you can see it ranges. In some instances we got none. In some instances we got as many as 9 false positives. Overall we got 464 false positives. So if you had this data in front of you, you could come up with 464 completely bogus relationships to talk about, and you could say, oh, it's statistically significant. But it's not statistically significant because the p-value, when they invented the p-value, they didn't envision that people would be running hundreds and hundreds of different analyses on the data. Let's try another way of making basically something out of nothing, p-value hacking. Let's fiddle with the basis functions, or as they're sometimes known, the specification of the model. Okay, here we're going to have very simple data. we're going to have x values between -3 and 3. We'll have y values drawn from a normal distribution, and we're going to tie the two of them together very lightly using a copula distribution. Don't worry about what that is, but it just manages to tie these two things together. And I'm going to produce 400 of them, and you'll see the results right there. Okay, so let's do your run-of-the-mill linear model fit on that data. You can see maybe there's a best fit line there, but boy, it's slender. Let's look at the parameter table, and evidently it's enough to say that there's a p-value. The effect is not big, but we do have a p-value of 0.002. If we just want the p-values, by the way, instead of using the parameter table properly, we can use the parameter p-values property, and we just get the one for the intercept term and the one for the x term. But we just selected these basis functions because they were simple. Maybe we'd like a smaller p-value, or maybe we'd like a bigger p-value. So maybe by changing the basis functions, we can change the p-value associated with the thing in front of the x basis function. So I'm going to create a little function here, polynomial bases, that create basis functions. And I think that the simplest way to see how this works is just to run it. So if I do a 4, it's going to say, give me up to a 4th degree polynomial as the basis functions. Or if I say 11, it's going to give me up to an 11 degree polynomial as the basis functions. So now what I want to do is I want to create basis functions, those polynomials as n goes from 1 to 5. And then what I want to do is to run a regression on them. Same data, different basis functions, same variable x, and get the parameter p-values. And I'm going to use something called association map. Have we seen this before? Well, let's just refresh. Association map, it's one of the many map cousins. Let's do it on U and A, B, C. And what it's going to do is it's going to create an association in which the second argument of the keys and the function applied to each of the second arguments are the values. And so it's often a good way of remembering sort of, here's what you started with, A, B, and C, and here's what you ended up with, UA, U of B, U of C. Okay, so with that, let's run this, and we see that here are our p-values associated. So for example, in this one, we have 0.778 associated with 1, 0.002 associated with x, and 0.468 associated with x squared. Now, what I want to do is a little bit of fiddling with this to get this in a form I'd like better. What I'd like to see is 1 goes to this, x goes to this, x squared goes to this. 1 goes to this, x goes to this, x squared goes to this, x cubed goes to this, etc. So to do that, I'm going to use something called key value map. I'm going to use association thread. This is sort of advanced coding that you do not need to really be able to replicate, but you can see what I managed to do. I converted each of these rules into themselves being associations. And now what I want to do is to use merge, which is going to say, okay, here's a list of associations. Put the values associated with x all together. Put the values associated with x squared all together. So we do that, and what we can see now is how the value of, for example, the p-value associated with the regression coefficient for x varies according to the specification. If it's it can vary anywhere from, this looks like kind of a low of 0, oh, here's the low, 0.02248, which is below a traditional 0.05, but here, as we increase the degree of the polynomial, the p-value in front of the x coefficient declines. And so if we want a high p-value, and to therefore be able to say, well, x doesn't matter, then we might want to use a high degree polynomial as our basis function. Whereas if we want x to matter, we might want to use a low degree polynomial as our basis function. And so by manipulating the basis functions, we can manipulate both the parameter value, the regression coefficient, and the p-value. So this is another form of p-value hacking. I just looked at how manipulation of basis functions could enable p-hacking in a univariate case. Let's now look at how manipulation of basis functions can effectuate p-hacking in a multivariate case. To do this, let's load in our famous Boston Holmes dataset. There it is. And this time we're going to use all the data. In the past we've just been using crime or maybe access, but now let's use all of it. Let's get all of the variables in this data set, the features, the covariates. So we're going to get the column headings out. I want them to be symbols for the moment. So we'll use toExpression to turn them into symbols. Don't get too worried about that. Now let's find out what each of the columns actually means for our edification. And actually, I don't want to redefine symbols. Let me remove that. I guess I had evaluated this earlier, but anyway. So that's what the various columns mean if you actually wanted to know the meaning of this regression. All right. Now what we're going to do is we are going to use most of the columns as our variables. We don't want the last column because that's what we're actually trying to predict. And for the basis functions, I'm going to use all of the covariates, most columns, and I'm going to prepend 1 to that. I'm not sure if we've seen prepend before, so let's look at prepend A, B, C, 1. Okay, so it just sticks it in front. So here are our basis functions. I could evaluate this in place, and so you can see what that produces. And we'll just run our friend linear model fit on it, and we will get a fitted model. I can then extract the parameter table from that, and you can see what variables appear to matter. So let's see here. Being near the Charles evidently has a positive effect on home price, and it's a significant positive effect. What else do we see? Dis, what is dis? Dis is the distance to 5 Boston employment centers, so I guess being away from the center of Boston is for some strange reason considered a negative factor. And so that's what we can see from the parameter table. But that's just when I used all the columns as basis functions. But maybe I could just use a subset. And if I used a subset of the basis functions, I might get a different result. In other words, I could just throw out some data and say, I don't want to look at the tax stuff or the racial composition or whether it's near the Charles or anything like that. And what's going to happen is these estimates are going to change. The p-values are going to change. Let's see how much. To do this, I'm going to define this little function through operator. Don't worry about it. The action here is right here, okay, before the slash the postfix. And that's why I use postfix a lot of the time. It's just sort of an afterthought or some cleanup. What I'm going to do is I'm going to take our covariate columns, meaning most of the columns, and what subsets does is it forms all possible subsets of those items in length 1 up to the length of the covariate columns. That should be length. All right. And just so you understand what subsets does, let's just look at what is the subsets of the letters from A to F of length 2 through 5, just for example. So those are all the possible subsets. Okay? So that's what we're trying to do, is we're trying to get all possible regressions that we could run using our covariate columns. So we do that, and there are all of our possible things. There are 8,191 possibilities. And we are now going to run 8,191 regressions. And we're going to use the same data throughout. We're going to use the same variables throughout. The only thing that's going to differ is that we're going to use a different subset. So here's a little function that creates the linear model fit based on a subset. And now let's actually execute that function on all of the subsets. So I believe I've shown you association map before. If not, you can look it up in the documentation, but it's going to create key value pairs between the things over which I'm mapping and the output from the function. And again, we've got our friend through operator, which is going to produce a summary of the output. The only other bell and whistle going on here is monitor. We haven't seen much of monitor yet. And the idea of monitor is when you have a long computation, it lets you kind of see inside and see what's going on, so you have some confidence that you haven't done anything dreadfully wrong. So let's run this. And it's going through all those subsets and running regressions. Can you imagine doing this on a calculator? I think we're getting closer. Well, I may cut the video here and bring you back when we're done. All right, we're done. And so you can now see we have an association in which the keys are the basis functions that are used, and the values are all the parameter table entries. From here on in, I do not expect you to follow the coding. Where I'm heading, let me just show you where I'm heading, is, I'm just going to run the code. All right. So where I'm heading is I want to get for each of the basis functions, crime, zn, whatever that is, indus. I want to know on how many occasions was the parameter, the regression coefficient, for example, small but significant, not significant at all, positive and significant, or negative and significant. And so to the extent that there is more than one entry here, as there is here, this shows that you can, by picking your basis functions, get at least one of these two answers. If I want it to be significant and small, I can get that. If I want it to be not significant, I can get that. Now, maybe I can't get it to be positive and significant or negative and significant, but at least I can get these two things. Let's take one where I have even a little more freedom with NOx. I think that's nitrous oxide emissions or something. I could have it be a negative significant factor. I could have it be a not significant factor, or if I have certain basis functions, I can have it be a positive significant factor. And so what we see is, here's one, DIS, which I'm going to have to look up for just a moment. What is DIS, do you suppose? Is it distance? Okay, weighted mean of distance to 5 Boston employment centers. Okay, so this is how far we are from the center of Boston. Perhaps I should have remembered that. But at least for a couple of basis functions, I can get it to be a positive significant factor. The farther you are away, the higher the home price. I can have it be small and significant. I can have it be not significant. Or I can have it be a negative and significant factor. It all depends what basis functions I use. And this is sort of the problem of regression hacking, is you're never going to see the regressions that the person didn't run. They're just going to present you the regression that they did run, and they may not even tell you they had data on the other stuff. So you have to be very careful when you confront a regression to find out, why are these basis functions being used? Were there basis functions that were available to them that they didn't use? And what would have been the results on those other circumstances? In fact, I'm now going to talk about defenses against p-hacking. And here's the deal. back in the days when the p-value was invented, back in the days of Fisher and sort of the classic statisticians, it was a decent form of protection against false positive results. Because you might have to do these computations by hand. And I don't mean by computer by hand, I mean really by hand, with pencil and paper and a slide rule and statistics tables. It was a difficult proposition. And so, in that kind of world where you can only do things maybe once or twice, getting a low p-value was pretty good protection that you weren't looking at a false positive. But in a world where statistical analysis is cheap, you just saw me doing 8,191 regressions in not very much time. Okay? The p-value no longer really provides that protection. They're manipulable through model specification, which we just saw, underpowered statistics, which we saw in an earlier video, treatment of under outliers, which we saw in another video. And so today, a p-value of 0.05 doesn't really mean that the probability is 5% that you would see a statistic as extreme as the one you do if the null hypothesis were true. Formally, that's correct, but it depends on the researcher not having succumbed to the very great temptation to experiment. And I've sort of cast the idea of someone acting in bad faith, but all I'm describing in some sense is an interactive discovery process and kind of seeing what works best. But the problem with seeing what works best is that it corrupts the notion of a p-value. And this is why there's a very famous research paper from 2005 titled Why Most Published Research Findings Are False. Maybe not that paper, but most published research findings are false. I've shown you some evidence on this point throughout the course so far. If you want to look at another great sort of exploratorium for looking at problems with p-values and regressions, 538, a sort of famous site, actually has some interesting information on that, which evidently I just turned to by mistake. So does this mean that you should just despair and give up and all statistics is nonsense? Well, I would say not yet. There are ways of combating p-hacking, particularly in a litigation context. The first is get that expert under oath and ask, did they run any statistical tests using alternative specifications? What were the results? Why are they presenting these results rather than those results? What did they do about outliers? Did they do anything with outliers? What processing of the data did they run? If you just look at the end product of a statistical expert, that expert can, if they're smart, they can manipulate the results to their heart's content. You need to look at the entire process from which that result was derived. Things that might make you suspicious are sort of a lot of variables that don't seem to be doing very much. Maybe they don't do very much. Maybe their purpose is to depress or augment a p-value. You ought to figure out, why are those variables in the analysis? What happens if you omit those variables? We looked earlier in this course at effect size, like the Hedges G statistic. And it's possible to get a low p-value where the effect size is small. And there is some suggestion in the literature that when you have small p-values and small effect sizes, that's a sign that there may have been some data manipulation going on. Also, if the effect size is small, you ought to suggest that, well, it may be statistically significant, but it's not practically significant. All right, you have the traditional things that you see in litigation about paying attention to financial incentives. There are lots of reasons science can be bad. It can happen because of bias, excessive zeal, even more likely incompetence, or using statistics as a black box and not really having a clue what you're doing, but just punching numbers into some spreadsheet. That can be disastrous. But where there's a lot of money at stake, like antitrust litigation, you ought to be particularly attentive to the results and see what choices the expert made in their presentation of data. What else can you do? Well, in machine learning, which we're going to come to shortly in the course, there's a different tradition. You don't tend to run statistical tests. Rather, what you do, as I've said before, is you train your model, you develop your model on one subset of the data, and then you see how it performs on data that it's never, ever, ever seen before. And if you get a result on the data that it's never ever seen before, that's a good sign. If your result collapses when you're confronting it with new data, then you probably have overfitting in your original training, and you need to go back and revisit. But if this training test methodology is done rigorously, then really, if you see something in the test data, that's a really good sign that it is going to persist. Now, you can subvert the training testing paradigm by sort of letting yourself peek at the test data. That is, you train your model, and then you see how it performs on the test data. And then if you don't like how it performs on the test data, you go back and you tweak the architecture of your model. And you keep doing that in a cycle. So what you're really doing, though, then, is you're training on both the training data and the test data, because the test data is being used, perhaps in a different way, to shape the model. So in a litigation setting, you want to ask, what steps did the researchers take to really put their test data in a lockbox? And if you look at Kaggle, which is an organization that runs machine learning competitions, one of their sort of specialties is really putting the machine learning test data in a lockbox. So you develop your model and you just do not have access to that data, and then they see how well you perform. If you don't see test data when you're looking at certainly machine learning stuff and maybe statistics stuff, or there's no lockbox, you can be suspicious. And you can also find out whether the researcher might have used the test data in some iterative process, which at least has the potential to lead to manipulation of statistical testing or machine learning findings. Another thing you can ask is, did the researcher register a hypothesis prior to significant work being done on the data? That is, what you might want to say is, I believe, here's my hypothesis, here's what I'm going to prove, here's what I'm going to use as the basis functions. And you register that in some place where you can't manipulate it using blockchain or something like that. Then you can see, did that hypothesis bear out? Now, that can be manipulated too, because you can do the work first and then register the hypothesis, but I'm going to assume that that wasn't done. What else does this tell us? It tells us you need to get the data. Sometimes judges deny opposing parties access to the underlying data, and they may deny them access to the draft, to the workflow. In my opinion, that is a huge mistake, because in the modern world, if you don't have access to the data and you don't have access to the process, you really cannot fully cross-examine the expert and determine whether their findings are genuine, the result of sincere science, or whether they are the result of hacking. Presentation of reports, as I say, without the underlying data is like direct testimony without cross, or a severely handicapped form of cross. It's just not, in the modern world, a good way of getting at the truth. So if you get the data, then you need to use all the tools at your disposal to see whether there are alternative model specifications, alternative treatment of outliers, alternative statistical tests that could lead to a different result. And in many cases, in fact, you will get a different result. So I hope this has been a helpful summary of ways in which one can manipulate p-values and statistical analysis in general. It comes towards the end of our discussion of statistics. We will be moving on to visualization and then machine learning in the course as we proceed in Analytic Methods for Lawyers.